Manorama Yearbook 2022. India and the World. Indian Human Space Mission Dr. Unikrishnan Nair, a distinguished scientist, Director, Human Space Flight Center, ISRO, Bangalore. Gaganyaan is the maiden human space flight project of India for carrying Indian astronauts to space and bring them back safely to a predetermined destination on Earth. The word Gaganyaan literally means vessel to space. The Gaganyaan has an orbiting module which has two parts, a crew module and a service module. The orbiting module will be lofted into space and injected into a 400 km orbit with an inclination of 51 degrees by a variant of GSLV Mk3, named as Human Rated Launch Vehicle. The crew module is the habitat of astronauts and it has many subsystems to protect human lives and to provide comfort. The SM will provide an all-orbit support to the crew module, including power, propulsion, storing of life support system resources. A new center named as Human Space Flight Center HSFC was created by ISRO at Bangalore in 2019 for sustained and affordable human space flight activities, and Gaganyaan is the first project of HSFC. Human Rated Launch Vehicle HRLV. The Orbital module will be launched by Human Rated Launch Vehicle, which is a modified version of GSLV Mk3 vehicle as shown in figure. The HRLV will be made more robust by adding many features like additional redundancy in systems, incorporating an integrated launch vehicle, health management system, improving structural margins, etc. Typical ascent and descent mission profiles are depicted in figure. Challenges of human survival in space. There are many challenges for human survival in space conditions. The hard vacuum in space of 10 to 5 to 10 to 7 Pa, temperature extremes from minus 100 degrees to 120 degrees, dealing with weightlessness of space, threat of galactic radiation as well as high energy impact of micrometeoroid or orbital debris are some of the challenges. These challenges are addressed by various design features. The hard vacuum is managed by providing a leak-tight crew module where standard atmospheric conditions are maintained. The pressure in crew module is maintained at 1 bar and the temperature is between 18 to 25 degrees Celsius. The relative humidity is within 30 to 70%. These limits are selected to provide comfortable living conditions for the crew. Life support system. The crew module has a pressurized cabin with a life support system LSS and that will provide everything needed for the comfortable stay of humans for a few days, including collection and disposition of solid and liquid waste. For short duration mission lasting for a few days, the resources like food, water, oxygen, etc. are carried in special metallic bottles and containers. The astronaut consumes about 0.8 to 1.1 kg of oxygen per day, drinks 2 liters of water and eats about 0.6 kg of solid food. The consumables are stored in suitable metallic bottles in the orbital module. The oxygen will be stored in a gas bottle at a pressure of 250 bar and it will be regulated and used inside the crew cabin. The food will be packed in airtight bags and stored in storage area in the crew module. The water will be carried in sachets with special mouthpiece for drinking in space conditions. Each astronaut will give out about 0.96 kg of carbon dioxide per day. The exhaled carbon dioxide odor emanating from food items, human body, etc. will be removed by passing the cabin air through special chemical bed containing activated charcoal and lithium hydroxide beds. The crew will also release per day about 1.2 liters of urine and 0.3 kgs of feces. The solid and liquid waste will be collected in special chemical treated bags, sealed and stored. The thermal environment inside the crew module will be managed by a thermal and humidity control system. The crew cabin air is passed through special heat exchangers which has special coolant and take the heat from cabin air, and the heat will be rejected to space through radiator panels mounted in the SM. The humidity will be managed by allowing the humidity in cabin air to condense at heat exchanger, and the condensate will be pumped and stored in special tanks. It is mandatory for the crew to wear flight suit during the dynamic phases, that is ascent and descent phases. The flight suit is a self-supporting life-saving system with its own oxygen supply and heat removal systems, and can support the crew life and more than 1.5 hours in case of any crew cabin life support system failure. The flight suit will be pressurized to about 0.4 bar with pure oxygen, and crew will be inhaling pure oxygen. All the activities related to thermal management, cabin pressure control, and air revitalization are automatically performed by the life support system through a set of sensors and a dedicated redundant controller. Space food. There are certain requirements for space food. The food should not create debris that may fly around. The food packet should be airtight for avoiding any stray odor in crew cabin. It must be easy to consume in space conditions. Food should be tasty and storable for a few days without degradation. There are calorific requirements apart from meeting the requirement of balanced diet. Again, the food should be appealing to individual astronauts. Each crew needs 3,000 kilocalories of energy per day. The food is usually contoured, processed to enhance its shelf life. Conventional food items like khatti roll, aloo paratha, vegetable pulao, suji halwa, paneer masala, chapati, dal fry, biryani can be conveniently packed and used in space. The beverages like tea, mango nectar, stored in sachets can be used. Also, energy bars, nuts, etc. can be used depending upon the crew taste and situation. Micrometeoroid and orbital debris. There are thousands of man-made and natural debris in space, causing many dangers to space vehicles and satellites. As of 2020, there are 1 trillion orbital debris with size greater than 0.1 millimeters moving at great speeds ranging from 7 to 15 kilometers per second. Orbital debris with more than 10 centimeters are well tracked and catalogued, and there are about 20,000 of them around the Earth. Whereas the details of debris below 10 centimeter size are difficult to gather, and hence special design considerations are implemented in the orbital module to take care of debris impact. The threat of debris impact is more for large objects like International Space Station because of its large area, and hence the more likelihood of debris impact. The methodology adopted in debris impact mitigation is to have a double wall construction. Upon impacting the first layer, the debris will be fragmented into many tiny objects, thereby splitting the kinetic energy of debris into multiple objects with lesser energy. The second layer will be able to better resist such impact of multiple tiny objects. It is always preferable to avoid any impact of debris by proper selection orbital parameters. Therefore, the threat of debris can be minimized. The debris for debris with size more than 10 centimeters, for which track information is available, the orbital module can be maneuvered using the propulsion thrusters in orbiting module and avoid any impact with the approaching debris. Radiation in space. There are many sources of radiation in space. The radiation dose will be different depending upon the orbital parameters like altitude and orbital inclination. Space radiation is made up of 3 kinds of radiation: particles trapped in Earth's magnetic field, particles shot in space during solar flares, and galactic cosmic rays, which are high energy protons and heavy ions from outside our solar system. Earth gets maximum radiation from the sun. The sun emits all wavelengths in the electromagnetic spectrum. Giant explosions called solar flares occur on the surface of the sun and release large amounts of energy out into the space in the form of X rays, gamma rays, and streams of protons and electrons. And solar flares can cause serious damage to astronauts and their equipment, even at locations that are far from the sun. Galactic cosmic radiation is a dominant source of radiation that comes from outside the solar system, but primarily from within our Milky Way galaxy. GCR is composed of the nuclei of atoms that have their surrounding electrons stripped away and are traveling at nearly the speed of light. The radiation is measured in millisievert, and astronauts are exposed to ionizing radiation with effective doses in the range of 50 to 22,000 MSV. 1 MSV of ionizing radiation is equivalent to about 3 chest X-rays. The walls of crew module will provide some amount of protection and radiation to the crew inside. The concern of radiation is more when the astronauts step out of the crew module for spacewalk or when they stay in space for longer duration like weeks or months. In Gaganyaan, spacewalk is not envisaged and the mission duration is only about a week. Hence, the radiation heat is minor in nature. The radiation levels will be monitored in the unmanned missions using special sensors, and this data will be used for taking decisions on the need of additional radiation shielding to the orbiting module. Weightlessness of space. An orbiting body is in a state of perpetual free fall under Earth's gravitational field. As weight is the reaction of the platform upon which someone is standing, under free fall there will not be any such action on the body as the body is freely from falling down. Hence, the person experiences weightlessness under free fall. This is sometimes referred as microgravity or zero gravity condition, as the astronaut is not feeling the effect of gravity even though he or she is falling under the gravity of Earth. Weightlessness causes several key systems of the body to relax as it is no longer fighting the pull of gravity. Astronauts' sense of up and down gets confused because the vestibular system no longer can figure out where the ground and the ceiling are. Crew members also experience a disruption of their proprioceptive system, which tells where arms and legs and other parts of the body are oriented relative to each other. This disorientation can make astronauts to feel queasy for some time. The long-term effects of weightlessness can create more trouble for astronauts if they stay in space for weeks to months. Calcium in bones secrete out through urine. As the bones weaken, astronauts are more susceptible to breaking them if they slip and fall, just like people with osteoporosis. Muscles also lose mass. The long-term research carried out in the International Space Station has helped NASA run studies on how astronaut health is affected with time in the weightlessness of space. The effects of weightlessness on body can be countered by doing specifically designed exercise in space, including cardiovascular exercise. However, the long term of weightlessness is not applicable to Gaganyaan astronauts, as they are spending a maximum of only 7 days in space. Gaganyaan, the Indian human space mission. The Gaganyaan orbital module has two parts: the crew module (CM) and the service module, as depicted in figure, and weighs about 8,000 kgs. While in orbit, the OM will be orbiting the Earth with a velocity of about 7,800 millimeter per second. After the orbital phase of flight, the OM will be reoriented for entry to Earth and it will be deorbited by firing the liquid propellant thrusters in the service module. The CM is a double-walled structure and is the habitat of astronauts. The CM is designed to re-enter the Earth's atmosphere and has an ablative thermal protection system to protect it during the intense aerodynamic heating during flight through the atmosphere. An ablating TPS mitigates the incoming heat through phase changes, chemical radiation reactions, and material removal. Is designed for the CM. During the re-entry, the temperature on internal surface of CM can reach as high as 1600 degrees Celsius. The TPS will ensure that the substrate temperature is not exceeding 120 degrees Celsius under worst case scenario. The temperature inside the crew cabin will be maintained at comfortable levels by the thermal control system. After deorbiting, the CM will be separated from OM and it will be continuously maintained in the required orientation through the closed loop navigation, guidance, and control system. In a controlled manner, the CM will re-enter the Earth's atmosphere. The CM has a cluster of small thrusters with 100 Newton thrust level based on green propulsion that will be fired in controlled manner to change the attitude of CM during the re-entry and atmospheric phases of flight. By virtue of its orbital height and velocity, the OM possesses huge amount of energy. More than 99% of CM energy will be dissipated through aerobraking while traveling through the atmosphere. Remaining energy will be killed by deploying a two-stage parachute system. The parachute will reduce the CM speed to less than 8 meters per second at splashdown in sea. Recovery from sea. The CM will be splashing down in sea near the Indian coast. The Arabian Sea is comparatively calmer and is the primary choice for landing. As backup, landing option is in Bay of Bengal also will be considered. After landing, the coordinates of CM will be passed on to the recovery team waiting in ships. The recovery team will approach the CM and the crew will be recovered. There will be redundant communication and location systems for easy recovery of crew from sea. The CM has survival packet for each crew that can support them for nearly 2 days. However, the crew will be recovered in nominal conditions within 2 hours after the splashdown. Crew training. The astronaut training is a crucial part of any human space flight mission. The crew will be familiarized with all conceivable situations that can happen while in flight and they will be trained to face such situations. The training will include classroom sessions on different engineering, medical, and safety aspects of the mission. The crew will undergo training in weightlessness conditioned by flying in special aircraft through a parabolic path that will give 25 to 30 seconds of weightlessness duration. In order to familiarize the crew with rescue under abort conditions, they will undergo special survival training in sea, snow, mountain range, desert, etc. They will be taught to survive in such situations, making use of the survival kit available with them. The crew will also undergo long duration training in special simulators that will mimic the interior of crew module. The training will address how quickly they can don and doff the flight suit, how to manually intervene under emergency situation to resolve the issue. For Gaganyaan, the selected 4 astronauts candidates have undergone generic space flight training at Russia for about 15 months. The Gaganyaan specific training will be carried out in India at the astronaut training facility being set up at Bangalore.